Okay. So the equations of motion for a rigid N-link manipulator can be defined using good old Lagrange's equation. So you get d by dt of di L di theta dot I minus di L di theta dot di theta I equals tau I, where I equals 1 all the way up to n, the number of links, where L is the L is the Lagrangian, so that's the kinetic energy minus the potential energy. Thank you. Does everyone have this diagram? L equals T minus U. Difference between kinetic and potential energies. Tau I is equal to the external torque. Which includes torque from electric motors is external torque. So even though you might think those are internal, but really it's an externally applied torque to the system. So theta are the link positions in angular coordinates. Just one thing to look out for when you're doing the dealing with the code that I gave you is that MATLAB likes to deal with all the angles in terms of radians, so to look at that can be kind of confusing sometimes. So just remember to convert it into degrees before you kind of look at the results if you want it to kind of make sense. So the kinetic energy is a little bit more difficult than just 1/2 mv squared because this is like a rotational system. So we don't just have translational kinetic energies, we have rotational ones. So it's the rotational dynamics that tend to be the tricky part, obviously, because everything's a little bit more complicated when we talk about rotating systems rather than systems moving in a straight line. The sum of translational and rotational terms. So it's 1/2 the sum from I equals 1 to n. The first one is the easy one, mv squared. And then you get the rotational one. Normally this is a inertia matrix. Normally we write it as a capital I, but in this course I'm using capital I to mean the identity matrix all the time, so I just didn't want to, I thought it might be a little more clear if it said J sub big I. It may or may not be better, but I kind of like I being the identity matrix all the time. So in this equation, little mi is the mass of link I. dci is the translational velocity of the center of mass of link I. My awkward J sub big I is the inertia matrix of link I. Omega I is the angular velocity of link I. And my big M is the inertia matrix of the system. Potential energy is due to gravity only. The external forces include joint friction and control input torque. And the motors. So tau I could just use a linear model of friction, a constant d times theta dot as a linear friction model, plus u. So I'll just always denote my controls as u, so that'll be torque in this case. By the way, I don't know if you have kind of come used to being a grad student now where you can always derive things in MATLAB symbolic math. But when you see me write something like that Lagrange's equation up there, like nobody's going to ask you to do that in a final exam, right? Like this is don't panic when you see things like that. Like that's undergrad thinking. Someone's going to ask you to do that in the final. That's scary. In this course, you see something like that, you're like, I'll just type it into MATLAB symbolic math. It'll probably fit an answer for me. That's exactly what it'll do. So you can confirm everything I'm writing on the board here quite easily with a few lines of code in MATLAB symbolic math. It's not a big deal. Theta dot times, or m of theta times m theta double dot plus c of theta and theta dot times theta dot plus d theta dot plus g of theta is equal to u, where gi theta equals di big U theta I is the gravitational torque on link I. C of theta, theta dot times theta dot is equal to m dot of theta times theta dot minus 1/2 di by di theta, theta dot transpose m theta, theta dot transpose. So there is no unique factorization of C theta theta dot. So I mean, this is a matrix, so this often happens when you have matrices, is things can be rearranged inside the matrix, and it really makes no difference because when you multiply that matrix by something else, it still gives you the same answer. So that happens in this case, where basically I could pick I could arrange these concepts a bunch of different ways inside this matrix, the C of theta and theta dot, and it'll still give me the same answer. But probably there's going to be one way to do it that's really handy. It's going to work out really well for me. So in this case, the best way to do it, if we choose the elements by Cij is equal to the sum from k equals 1 to n, 1/2 di mj di theta k plus di mij di theta j minus di m I k di theta I times theta j dot times theta k dot. I'm not going to explain why this is the case, but if you do it this way, then it works out nicely. Then the matrix one-half m dot minus c is skew symmetric. So what does skew symmetric mean? That means that x transpose 1/2 m dot minus c x equals 0. So we kind of have a physical interpretation of this. So the physical interpretation of this result so the term C theta and theta dot times theta dot contains Coriolis and centripetal forces. And the thing about Coriolis and centripetal forces are quite different from other kinds of forces because they're basically fictitious forces. So if you're riding the robot, you feel these forces just as much as you feel any other forces as a sensation, but they're not actually doing any work. So friction does work. It slows the robot down. Friction slows things down. It's obviously doing work. So it's creating, kinetic energy is getting turned into heat when friction occurs. So that's like work happening to the robot. Obviously, the electric motors are doing work to the robot. They're obviously adding energy. So centripetal forces, Coriolis forces, are forces that you feel if you're riding around in the robot because they'd be throwing you around like a roller coaster or something. but they're not actually doing any work on the system. They're not making it go any faster and slower overall. Not adding any energy or taking any energy out of the system. So which are forces that are felt by the robot? I want to anthropomorphize the robot, which I do, but do not do any work. I.e., these are usually called fictitious forces. So hopefully you still learn about Coriolis and centripetal forces in high school, even if you have an electrical engineering degree. Probably took that in grade 12 physics or something, right? Really?
I don't remember taking that.
They don't teach Coriolis forces in grade 12 physics anymore?
Centripetal, I think, but I don't think Coriolis.
Centripetal? Is this centrifugal?
Well, centrifugal is not considered a term in science. Scientists will jump up and scream if you use the word centrifugal. Centripetal is what you're supposed to say because it's the force that pulls you in. Centrifugal is like an idea that you feel like there's a force pushing you out. So nobody ever says centrifugal, but it's the same idea. But they don't talk about Coriolis forces. And anyway, Coriolis force is like the force that creates like a hurricane. The Earth's rotating and it's rotating at different speeds depending on what latitude you are in the Atlantic Ocean. So it creates like a spiral pattern for the hurricane. Basically, it's a force you feel when there's different velocities at different parts of the robot arm, right? So each part feels like it's going at a different speed, which creates like a torque. It's the same torque that creates a hurricane, basically.
Read through electric machines.
Sorry?
In electrical machines, we read.
You read about Coriolis force in electrical
Yeah,
machines?
yeah.
Good. So let's do an example, a two-link planar robot. So those are the lengths to the center of mass, hopefully kind of obvious. So LC1 is the distance to the center of mass. Of link 1. From the shoulder joint. So hopefully it's obvious what's the shoulder and what's the shoulder and elbow is what I'll say, but it's probably obvious. So same for, so I'll just say likewise for LC2. I guess I'm using fancy L's here. LC1, LC2. So the kinematics is your mapping from joint space into the Cartesian space. And usually you're a lot more interested in what the robot is doing in terms of the Cartesian space than the joint space. So this is probably the coordinate system you're actually designing for when you're trying to get your robot to do stuff. So hopefully it's pretty obvious that x would just be L1 cos theta 1 plus L2 cos theta 1 plus theta 2, where L1 and L2 are like the total length of each link. L1 is the length of link 1. Things are kind of messy if I put it on the diagram, but y equals L2 sine theta 1 plus L2 sine theta 1 plus theta 2. So that's just simple geometry. Hopefully that's pretty obvious how I came up with that expression there for x and y.
Should that be L1? Y is equal to L1.
Oh, sorry, yeah, thank you. So kinematics are a static relationship between joint angles and Cartesian coordinates. Dynamics are actually talking about the differential equations, the equations of motion, how things are changing in time. So let's to derive this, we have to derive some expressions here first. LC1 is equal to XC1 is LC1 cos theta 1, and YC1 is LC1 sine theta 1. XC2 is equal to L1 cos theta 1 plus LC2 cos theta 1 plus theta 2. And YC2 is equal to L1 sine theta 1 plus LC2 sine theta 1 plus theta 2. So the velocity in Cartesian coordinates, which we're going to need for our kinetic energy expression. So we get VC1 is equal to XC1 dot, YC1 dot equals JC1 theta dot, and VC2 XC2 dot, YC2 dot equals JC2 theta dot. So obviously I can differentiate these expressions here and fill them in here and get this and this. So JC1 is equal to negative LC1 sine theta 1, 0, LC1 cos theta 1, 0, and JC2 is equal to negative L1 sine theta 1 minus LC2 sine theta 1 plus theta 2 minus LC2 sine theta 1 plus theta 2. Here we get L1 cos theta 1 plus LC2 cos theta 1 plus theta 2. L2 cos theta 1 plus theta 2. So we need these for the translational kinetic energy, because translational kinetic energy we can do basically in Cartesian coordinates. It's the easiest way to think about it. So the translational kinetic energy is one half M1 VC1 transpose VC1 plus one half M2 VC2 transpose VC2. So that's one half theta dot transpose M1 JC1 transpose JC1 plus M2 JC2 transpose JC2 theta dot. So you can kind of see that this is, definitely depending on the particular robot I picked. I'm doing this example of this two-link planar robot. Obviously, you're going to get quite different expressions here if the robot has different kinematic configurations, right? If you have more degrees of freedom and the robot has more links and things like that, it can be quite complicated. But again, you wouldn't drive by hand, you just type in code and ellipse-symbolic math to drive the equations, so it's not that big a deal. And most standard robot configurations have already been analyzed somewhere where you can check your work to make sure that you did the right thing. It'd be very strange nowadays to come across a robot design where someone hasn't already derived all these equations, right? You have to have kind of a very particular design in mind for that to happen. So for this robot, angular velocities are aligned in the z direction. So the rotational energy can be written one half I ZZ1 theta 1 dot squared plus one half I ZZ2 theta 1 dot plus theta 2 dot squared, where IZZ1 and IZZ2 are the moment of inertias of link 1 and 2 with respect to joint 1 and 2. So these are the kind of numbers that are kind of annoying to come up with in the first place for a robot, but for the robot that in the lab, the company sent me the robot with these numbers already filled in the code they sent me, which I'm sharing with you, so it's nice and easy. We already have all these numbers for this particular robot, so we don't have to worry about that. You can try and come up with something like that experimentally to try to measure the moment of inertia, but if it's like, if something's like a bar or a cylinder, you have to integrate, but then again, everyone's done that already for you, so you just actually look it up somewhere. Right? There's all these formulas out there for moments of inertias of all geometric objects that you can just look up. Yeah?
Sorry, this was in terms of link 1 multiplied by 2.
Link 1 and 2.
One.
Yeah. So for example, the moment of inertia of a ball on a string is just 1/2 mr squared, right? Mr, where r is the length of the string, m is the mass of the ball. If you're assuming the string is massless, it's just 1/2 mr squared. So it gets more complicated when it's like a cylinder or a bar or something. Sorry, did I say 1/2 mr squared? Is it energy? No, mr squared. Mr squared, not 1/2. So the sum of translational and rotational energies is 1/2 theta dot transpose m of theta dot, where m is equal to m1 jc1 transpose jc1 plus m2 jc2 transpose jc2 plus this matrix of izz1 plus izz2 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 izz2.